Let's dig a little bit deeper into designing algorithms, evaluating algorithms, and debugging and improving upon an algorithm. One of the first questions that we want to answer is what makes a good algorithm? There are some things that it's pretty easy to get everyone to agree upon, and we'll deal with those first. And then there are some different angles that may be argued are more or less important by different people or in different situations. But almost anyone thinking about algorithms could agree that a good algorithm design should have statements that are well ordered. It should be clear what happens first, what happens next, and so on. The statements that are made should be unambiguous. There should not be any room that's left up to interpretation, because quite often when you're designing an algorithm, you may be handing it off to someone else to implement, or you may be trying to share it. For instance, publishing algorithms in a research publication, where it's pretty important that someone be able to look at that and figure out the order that you want things done in and the specifics of how they're going to be done. It should be relatively close to code in that respect, that code has one way to execute on a particular line. Even if it's conditional, there's one way to execute for a given set of conditions. And likewise, your algorithm should be about as detailed. And an example of this is that each statement should be easily computable. So, for instance, you should not say something in your algorithm like, search the internet for the best product. This is a pretty complex step that really should be filled in. Now, it would be fine if you had defined previously a function for doing that would specify what the best product is. Is that the one that ships fastest, the one with the best price, the one that looks prettiest? If you can evaluate it computationally, then that should be specific exactly how you're going to do that. And in the same way, there shouldn't really be subjective things left in there. Find whether the book's plotline is good. Well, that's not a computable statement unless you define a metric for what determining a good plotline computationally looks like. So every statement that you make should be something that's easily computable. Basically, if it's a statement in your algorithm, you probably ought to be able to do that one-line statement in one or only a couple of lines of code. Your algorithm should produce the correct result all the time. It should handle those strange cases that may not be particularly desirable, but are possible to happen. Negative values, zeros, things like this. It should handle them with some amount of grace. And the correct result may be a message to the user that says, that's not a valid input. But in many cases, a correct result is pretty well defined. If my algorithm is supposed to find me a route from point A to point B, then that route ought to actually get me from point A to point B. And that route should fit whatever qualities were determined were good and required from the algorithm as well. Your algorithm should also complete in a finite amount of time. It should not take forever for your algorithm to run and solve the problem at hand. And this is where we should avoid things like infinite loops and anything else that will cause our program to just wait forever, like waiting on a network connection or user input that may never come. Some general rules to follow are simplicity, clarity, and generality. Generality meaning that an algorithm that you write should handle the full range of possible things that fit its problem scope It shouldn't be very, very narrow to only a small subset of those if it's going to be applied to that full range of problems, possibly. Now, when it comes to evaluating algorithms, saying which one is better than another, or is an algorithm good enough, or things like that, this is where we get into often some debate, or where we may have to balance some features against other features. One that's really pretty important is correctness. As discussed before, your algorithm should come out with a correct result, and it really ought to come out with a correct result all of the time. There's some leeway for this in bigger problems, or where results may not always be possible based on the conditions. But generally speaking, an algorithm should be providing correct results. However, often there is debate around the quality of result. For instance, thinking of that pathfinding situation, is it important that my algorithm give me the fastest route from point A to point B? Is there some acceptable amount of deviation from the fastest route that I'm willing to accept if the algorithm is good in other ways? So what other ways might an algorithm be good? It might be good in the ease of understanding what the algorithm is doing. Many of the algorithms that we use nowadays, like say the recommendation systems on social media, are really not written to be understandable. And humans are not really sure why the things are popping up that pop up. Similarly, simplicity or elegance indicates sort of this, is it easy to take that algorithm and put it into code? And is it straightforward again in some way that makes it easy to be pretty sure that you wrote it the right way? For instance, there are quite often times where a very complicated algorithm may be very good in a lot of other ways, but it's so hard to implement that people often get it wrong, and therefore it's not very usable and may lead to people actually getting wrong results from what they thought was a correct implementation because the algorithm was overly complex. It wasn't simple enough. And another metric that's often used is efficiency. Will this algorithm find me an answer quickly? If we go back to our pathfinding to get from point A to point B, an algorithm that gives me the absolute best result, one that no other algorithm is going to give me this good of a result because it's analyzed traffic conditions and it's used current weather satellite data and it's, looked at all of these back road routes and everything else. That algorithm may take so long to find me a route that I'm not actually going to be interested in using it. So it's good, according to one metric, of giving me a very high quality solution, but it may be bad enough in terms of efficiency that I don't care to try to use it. And similarly, space, meaning the amount of memory and storage that's needed for an algorithm, is another metric that we might measure an algorithm against. If it takes up so much memory that I have to buy a giant supercomputer to run it, then perhaps the average user is not going to like that algorithm, and perhaps if I build it into my piece of software, no one's going to buy my software because my software has such high demands on their system. And so we often, when evaluating algorithms, have to look at these different aspects of the quality of that algorithm and balance them against each other. To revisit a little bit of what we talked about with software design principles, some of the same ideas are true for this more general algorithm design idea, and that is working through the design of the algorithm multiple times, at least twice, because as you think the algorithm design down through the first time, you will start to see more bits and pieces that are required to meet the specification. So you'll start to think up, I'll need to write a function that handles this kind of piece of the problem. And I'll need, at some point, to loop through the data and clean it up to make sure that these features are not present in the data. For instance, no negative values or no zeros that I might divide by. So then, as you redesign and think through further, you'll start to be able to put those pieces together efficiently and effectively. You might start to see that this function needs tweaked in a certain way so that it pairs better with the function that's going to be using its results as their input. It's really hard to put anything together in an orderly fashion if you don't already know what all of the component pieces are. So often that first algorithm design step is sort of high level, thinking through maybe in ways that wouldn't even qualify for some of our design statements earlier, that a single statement should be easily computable. Well, at your first pass, you might let some of those slide. I'll find the best product somehow. I'll worry about that on my redesign, my second design phase. And you can keep a list of the parts of your design that still need some details filled in when you come to do a second or third or however many passes through the design as you need to be able to get it down to this pseudocode clear design level. And just to reiterate, simplicity in algorithm design is extremely important. In particular, as I hinted at before, creating a simple and straightforward algorithm helps to improve the reliability of that algorithm. That you know that you can analyze its performance very well, you can implement it in code in a way that's easy to see that it matched to the algorithm as it was designed, and you can share it with others in ways that they'll be able to understand and to use. So here's an example of some pseudocode. You may notice that it looks pretty similar to regular code. This example even uses some Python keywords in it that you may or may not choose to use in your own pseudocode. This demonstrates that this is a function at least, but it's a little specific to Python, so many people would eliminate that kind of language-specific detail from it. But what pseudocode does is it helps you to structure your design similar to the way that that design will look when it's implemented in code. But you can see that some of these statements are still not quite filled in with the details of how you would do this in code. For instance, printing the word fizz with no new line. Well, that's sort of a note there to that, but it's not going to function as code. You're going to have to figure out, if you're the programmer handed this design, how to make it print without the new line and how to make the other ones print with a new line. Likewise, there's a statement, if I is divisible by 5. Well, again, you're going to have to, as the programmer, figure out how you can check if a number is divisible by 5 in the language that you're working in. Many times you'll see other things like create an empty list or add something to the list. Well, in different languages, adding things to lists or creating lists will follow different specific syntax and might even take a couple of lines. But in pseudocode, we write it as one statement that's general enough that it could probably be implemented in lots of different languages. The types of things that you'll see in pseudocode are sequential statements, like input, doing computations, and output, conditional statements, like our if-elses, Iterative statements like looping with for loops, or we'll later see while loops. And storage, meaning variables. But the way that those variables are expressed may be different than the details of exactly how they're done in the language. Another example of this is the loop here for I equals 1 to 100. Well, again, this is not going to be exactly how it works in the language, but it shows us enough. Our functions should show us their names, their parameters, and maybe even something about what they return or the body of what they do. And our loops and things like that should give us enough that in whatever language we're working in, we're able to turn the pseudocode into actual code. So here's an example problem that we may get some time to look at in class in more detail. But thinking through design, some of this steps back to our previous thoughts on software design from our earlier notes. But if we have the Conditori coffee shop, which sells coffee at $10.50 a pound, plus the cost of shipping, if each order ships for $86 cents per pound, plus $1.50 fixed cost for overhead, then write a program that calculates the cost of an order. So we would want to consider the inputs that are possible for this program. And we want to consider, again, a range of possible inputs. So think of small numbers, think of large numbers. I would argue that an important input to consider for your algorithm here would be the input 0, because it's going to be a special case, and you always want to try to think of those special cases and how you're going to handle them. If someone gives you a negative number, for instance, that's relatively easy because you're going to just ignore it or give them an error message or something like that. 0 might slip past you if you're not very deliberate in choosing the inputs to consider while you design, because 0 times 86 cents will give you $0 in terms of this part of the shipping cost, but we would still charge the person $1.50 fixed cost. Oh, and likewise, 0 times the $10.50 a pound. Well, again, that would $0. So this seems good so far, but we would end up, if we didn't take 0 seriously as a possible input, charging the person $1.50 fixed cost for a shipment of nothing. And so when we consider inputs, it's very, very important to consider categories of inputs the best we can. Like I say, often examples for numbers would be small ones, large ones, zeros, negatives, whole number values versus fractional values in some cases. Here, that doesn't matter too much, but it might still be worth testing a couple like that. Then we want to think about the return value and or side effects that might happen. So the return value in this case would be the amount of money that the person owes for the given input of an amount of coffee. So we would have a pretty clearly defined return value here. It's a number, some dollar amount for the amount of coffee that they've bought. The side effects can sometimes be a little less clear. Side effects are things that happen in addition to or instead of the return value. Examples of side effects would be, well, printing to some extent, but especially things like changes to files on our system, changes to data structures like lists. If we removed something from a list in the middle of our function, that could be a side effect. If it exists after the function is over, then that could cause important side effects. And it's critical to think about your program's impact in a larger scope like that. Will this function change the data structures that are passed into it? Will this function change something in the operating system or in the file system that it's running within? and make sure that those side effects are well documented so that our users know what's going to happen from our code, from our algorithm being run. Then we think about what the basic structure of the code would be. So then we start to think about things like that we'll need to calculate the cost of the coffee itself. Then we might need to calculate the per pound shipping cost. And then we might need to add on that $1.50. And because we thought clearly about our inputs at the start, then we're going to know things like we might need a special case when it comes time to add that $1.50 on for if the person ordered nothing, if they canceled their order, said no thanks instead. Should we use one function or several functions? Some of these become sort of a personal choice thing. I would argue that functions that are one short line are not the most useful of functions. So if your function is just taking number of pounds times $10.50, that might not be a very helpful function. It's going to add more to your program than it actually saves by having that function. Reusability and clarity are kind of the keys when it comes to functions. So it is very reusable to have a function that does just this whole job. $10.50 times the number of pounds, 86 cents times the number of pounds, and then possibly the $1.50 fixed cost for overhead, adding them together, that's very reusable. And it saves some code if I have to use that in several different places. Say the person orders 3 different types of coffee or has a repeating shipment of coffee or something like that. And then we think about how we can test it. Because our job is not done just because we wrote the code. It is extremely important to think through how we test. And usually the answer of how we can test it has a lot to do with the early questions we answered. What are the inputs? What are the expected return values? And what are the expected side effects? We would want to make sure that if I give it one of the particular expected inputs that I had thought through, that I get the matching return value, and that the side effects that happen are only the ones I documented and anticipated, that I don't end up deleting data that I might need later in the program, for instance. So when it comes to testing, that's where we're going to encounter the bugs in our program. In your labs, this will be through doing your own testing, writing print statements or writing calls to your functions, and validation. It's very important that you run the validation on your labs to see what errors come up because we've written tests already. It's also very important that you think through your own ways to test your functions, like thinking about what good inputs would be and what the expected outputs would be for each of those inputs. So if you find a bug or if you discover that your program is not doing the job that it should do, bugs will come in the form of error messages sometimes, and in the form of just bad behavior. You get a negative shipping cost amount out of your shipping calculation function that we were discussing before. That's bad behavior. It won't cause an error message. Your program will keep running, but it's probably not a great idea to be signing off checks to your customers for their shipping costs when they ordered positive amounts of coffee from you or things like that. So you reread the specification that you created and documentation about any code that you're using. Either documentation that you wrote about the code as you wrote your parts of it, or things like documentation in the Python libraries that you might be using. If there is an error message, it's important to read that error message clearly, see what it indicates to you, what parts of the code it points you toward. Those may not be the line where things started to go wrong, but they will certainly be a line where something went very, very wrong and was discovered to have gone wrong. In the example of getting that negative value, it may be the case that at some later point, you actually have an error because you were using that negative value to try to get an item from a list and it was too far negative, or the number you're getting is beyond the range of the list, or things like that. So the error may actually be that you calculated the wrong index somewhere, but you'll get the error message at a line where you tried to use that index. Well, that gives you information. Can't always fix the error right at that line, but you can figure out what's going on. And that's where examining variable values can be very, very important. There are many different ways to do this in programs, and as you get more skilled at programming, you'll learn to use things like built-in debuggers that will show you the variable values as the program runs. For now, probably the most straightforward one is just to print out what different variables are and where your execution of your code has gone if you have things like if statements or loops. It may also be helpful to talk through the issue that's going on, even to yourself or to an imaginary person or an inanimate object, just describing in detail, line by line, what you think should be happening and what you see happening. And you may also talk to another person who can give you some feedback and ask you questions and help you to think through where things might have gone wrong. Let's look at a few common error messages that you may have already seen or you may see in the future. Here is a function definition in Python, and we're getting from it this error message. So with this error message, believe it or not, you can see what the error is that you're having and which line has an error. So it'll indicate to you which line it first noticed the error. So it noticed it on this line. And it says invalid syntax. Sometimes you will get these errors a little further along in your code. For instance, if you forget to end a parentheses, sometimes you will get the error at some later point where it's saying, by now we really should have seen an end of parentheses. I'm not sure where exactly you want it, but I know that by now there should have been an end of parentheses here. But in this case, the error tells you exactly where the issue is. The invalid syntax is that you tried to define a function and you didn't put a colon character at the end of the first line of the function. So this is a very helpful function if you know what it means, but of course this is sort of like speaking another language for a moment. What is invalid and what in the world does syntax mean? If you know that syntax means the required wording and structure of your program, then you might look at that spot and say, I've written something wrong in terms of what Python requires in this type of statement. In a def statement for a function, it requires a colon at the end of the line. This error message also tells you what error you're having and which line has the error. And again, it may require some translation. So it says it's an index error. That starts to give me some hints. Indexing, we know that that's something that can be done with lists. We'll later see it in reference to other things too. And here it tells me this line number 2 there, is where the error is happening. It's even put a little arrow there to help to indicate this. So somewhere in this line, there is an index error. And specifically, that index error, the issue is that the list index was out of range. Okay, so then I can look at that line. Now, sometimes in the same line, I might have done multiple indexes into multiple lists. And so this still can take some determining what exactly is going on. For instance, if I had my list index 4 and other list index 0 and third list index 2, and I was adding them all together to get X, well, then I'd have to examine those 3 different lists and think about the index that's being used for them. Here, I'm only indexing into one list, and that list has 4 items, and this is a really, really common error. If I want the 4th item, I think, oh, I'll put index 4 in. But of course, the indices here are 0, 1, 2, and 3. And so 4 is outside of the range. There is no index 4, and the program errors at that line. Here's a little bit of a trickier one to translate. Yet again, it tells us what line to look at. But there's nothing that looks wrong about this statement, z equals x plus y. I've seen that in math classes an unlimited number of times, just about. And it tells me it is a type error. So that's an error with the types of data that I'm trying to use. The type error here is that I've used unsupported operand types for plus. So this means I gave plus two things that it doesn't know what to do with both of them. In particular, I've given an integer, a number, the number 13, and I've given a string, the word dog. And I've asked plus to add those two together. But in Python, that's not well defined. Should it be 13 dog? Should I add the number 13 to the number that D would correspond with in the alphabet and try to shift that letter forward by some amount? Should I turn dog into a number and try to combine that with 13 somehow? This is not well defined. So operands means the things that were given to an operator. Plus is the operator, a mathematical operator here, and they're unsupported. Python can't support this. I haven't defined how those two things are going to be added, and it would be a little difficult to define it in a general enough way that it would make sense all of the time. Here we have a function that's defined, and that function is defined well. When I go to call it, we see there's an error. It's another type error. Now, this could be especially confusing because you might start to think, did I give it the wrong type of data? Well, 4 and 3 are things that could be added, so that's perfectly fine. I'm not seeing what's wrong with the types here, but it tells me that I'm missing one required positional argument. What this really means is I'm missing one parameter. MathParty takes 3 parameters, and when I called it here, I gave it 2 parameters. It tells me even the name of the parameter that I didn't give a value for. Now, this could be tricky because maybe I intended 3 to be the value for z. But if I forgot to type in the y value, for instance, I've technically only given 2, and it will just assume those were supposed to be the first 2 parameters, and it'll tell me, you didn't give me anything for the third parameter. I'm missing one required parameter, one required positional argument. So some more translation gives us the information we need. We add a third value in, and everything should be fine, usually. Here we have another error. It is a 0 division error. I've attempted to divide by 0, and it's telling me I attempted to divide by 0 here at the line x plus y divided by z, which is a little confusing to me because I said z. Z is not necessarily 0, but Python is kind enough to give us what's called a traceback. I can look at the bottom thing and see what was most recent. What was the last part that errored? So the error actually occurred when I got to this line, the return that wants to do a division. But it tries to help me say, you're going to have to look a little further back before that line to find exactly what caused this error. So it's telling me, you know what? You tried to call MathParty with 430, and that's how I got the values for x, y, and z that caused the error at this return value here, or at this return statement here. And if we look again down at the bottom, it reiterates that this is a division by 0. So now I can kind of trace forward, again, 4, 3, 0. So x is 4, y is 3, z is 0. And now when I come down to the return statement line, I know I'm doing 4 plus 3, so 7, that's safe, divided by z's value, which is 0. That's why we have an error. So you can find which line encountered the error. You may also have to dig a little further in the trace here and see where the error happens. Sometimes it will be even at a different line from there. For instance, if I was using variables, instead of 430 here, I had A, B, C that had gotten their values somewhere further up in the program. Python may not always be able to tell me where to look further back and further back and further back. But it will do its best to show me, for example, the function call that happened that led to the error inside of that function. So if you've got an error that you're not sure where it's coming from, in that example of the A, B, C there, that I'm not really sure where are A, B, and C getting their values, or what are their values right before the function is called, or things like that, then one thing we can do is look at the values of different variables and look at what pieces of our code are getting executed, where we are in the program at different times. Here's a program that's intended to check whether a coin flip came up heads or not. So the coin flip is done by a random choice of heads or tails, and that result from the random choice is fed into the checkheads function. But what I might notice if I called this flip heads check over and over again is that I'm always being told that it is not heads. So if I tried several tests, which this does not show any tests, if I tried several tests of this flip heads check and I returned is heads and I saw that is heads is always coming back false, then I would need to try to figure out where things are going wrong. There's not even an error in the sense of an error message being generated here, but there is a bug in the sense that my program is not going to come out with good results. Of course, you want a coin toss to be around 50-50, at 50-50 on the order of an infinite number of coin tosses, and this one just isn't doing it. So what I would do is I would have to think about where the print statements might go in this to see what's happening and what's going wrong. So a couple of things that occur to me is maybe the input string is not what I expect it to be. Maybe, for instance, I'm always coming back with an empty string somehow. I don't know how, but that would be useful information to know. So let's print that input string as soon as we get it. First line of the function, we'll print it and see what that parameter value was. We then could see whether we get inside our if statement at all. Because maybe the return's just not happening. And this does sometimes happen, that like you just didn't actually get the return to return what you wanted it to. And so we'll print whether we made it into the if statement or not. And then if I had some tests of this flip heads check, then I could see what their result is. And if I were digging through this, I would see a couple of things here. One is that in string is always capital H heads or capital T tails. It is never lowercase h heads. So it will never come back true. Then I might still have further debugging to do. But at the very least, I could have found part of the bug, and these help you to be sure that it is a bug. Without really examining the conditions of your program, often programmers, especially beginning programmers, just try changing things somewhat randomly What if I change this double equal to a single equal? What if I make it head instead of heads, or whatever? What if I make it return quote true instead of the keyword true? Lots of different things that you could change about this that will actually make it worse in many cases. So it's very important that you look deliberately at what the values are and what parts of your code are getting executed so that you can be sure that part is working. Because this code actually has even a further bug that flip heads check doesn't return its result. And so you could spend forever trying to fix check heads if you don't look deliberately at the value of the variables inside of check heads. You might think the error is in check heads forever. Once you've narrowed down that you got check heads working, that it is going inside the if statement, and that it is returning true in the right cases, then you might start to think that the error is in flip heads check, and you might notice that you forgot to return. If you print the results of flip heads check, you're going to see that its result is always none, and you're going to start to be able to debug that function too. Often your bugs are multi-error kind of bugs like this one. And so it's very important to test portions of your code. Test check heads on its own. Feed it just the word heads. Feed it just the word tails. Make sure you get the result that you want from it, and then move on to find a bug elsewhere in your code once you're sure that check heads fully does its job. So altogether, if you design an algorithm well, making clear pseudocode that has unambiguous statements that can be easily translated into code, that should reduce the number of bugs and errors that you have in the first place and give you a better quality algorithm. But there is still always room for making mistakes or mistranslating that algorithm design into code. Examples we've seen are incorrect indexes typed in, lower cases versus upper cases, single equals versus double equals, lots of things that you could get wrong. It's important to be able to tell what errors are telling you inside of a Python program, and that will take some practice and possibly looking them up as issues come about, or checking in with someone who's got more experience and information to help you figure out that error. But it also can take deliberate examination of the execution of the program, finding what the variable values are at different times, and finding what portions of the code are getting executed and what portions of the code are not getting executed under different conditions. And understanding that errors and bugs may be complex. And if we just hack around and try to change different parts without deliberately examining what's going on, and without revisiting the design that we initially came from, then we will often just spin our wheels indefinitely. And so it's very important to make sure that you test all the components of your code and that you understand how they're behaving as the program executes.